In this video, I'm going to go in depth on the AlphaDog vintage distortion, break down the whole schematic piece by piece, and even look at the board layout. So here we go. First is the input stage. We've got a current limiting resistor and a coupling capacitor. All that is about preventing DC voltage from bleeding out or having any sort of charge on this capacitor bleed out quickly and causing switching issues, pop, or just issues with other pedals. Then we've got some resistors that are setting the bias of that op amp with a 1 NF capacitor pulling, providing a capacitive load on the input. The reason for that is because this has a lot of gain, and if you just drive the gain on this op amp, it will start to self-oscillate unless we load down, put some capacitive load on that input. Feel free to experiment with that value. I found 1F is kind of like the sweet spot of keeping things, fairly bright on the top end without, self-oscillating. I do want to note that there's some empty pins up here. The AlphaDog is one of the very few of the new designs that doesn't use a charge pump at all. And so if you receive an SPS board with the DC converter soldered on, you'll want to remove that chip. And if you have a board that's empty and you're populating it from scratch, you won't install the charge pump components. That's it. Let's go ahead and go to that next stage. Okay, here's the main gain stage in its entirety. So it's a non-inverting op amp design. So here's the feedback loop, and this is what's being shunted to ground. We'll go into that a little bit here, but first I'm going to talk about the chip. This is from the data sheet. This is the LM308 precision op amp. And one of the things that's unique about it, it's got this compensator cap. And what that capacitor does is as the frequency increases, there's a little note here. It says it's proportional to 1 over CF, meaning, not as frequency, as the capacitance increases. What ends up is the bandwidth gets more limited and the slew rate slows down as you increase the capacitance. What that means is that essentially high frequencies response starts to weaken the larger that capacitor. So you can play with it. It will have impact on both the high frequency response, but also kind of the distortion characteristics, like how when it starts to distort, because the chip itself does a lot of distortion, especially if you put the soft control to 12 o'clock. So it'll affect that. And so there's a lot of Proco-RAT, this is what the whole circuit's based around, clones and mods and derivations that mess with that. So feel free to experiment. 33 PF is picofarads, what's in the AlphaDog and Proco-RAT, but feel free to 100 PF, 68, 47, like all sorts of values there. Okay, now I do want to point out this is a non-inverting op amp. So everything in this, from the output to the negative, if that resistance or impedance is higher, that increases the gain. And anything here that's getting shunted to ground, to ground here, it's the opposite. So the less the resistance or the impedance, the lower that is, the higher the gain. So here, more resistance, more gain. Here, more resistance, less gain. So it's the opposite. I'm not going to go into more detail than that, but there we go. I do want to point out that there is a alternative chip called the NE5534. I think AP, if you do that, you can find like a literally drop-in replacement, pull the old chip out, drop the other one in. And it's just, it's very similar in terms of its kind of overall pinout. It's not exactly the same, but it's compatible. And it just has a faster slew rate. And so it ends up having like a brighter tone and like a more crisp. Anyway, feel free to experiment. And we'll get to a little bit about that later, about how you do that. Let's go back to here. I'm looking at the main gain stage again. So first we're going to zoom in on this part. Remember, in this section, higher impedance or resistance, more gain. In this section, higher impedance resistance, less gain. Okay. All right, now in here we've got a capacitor that goes through this section. A capacitor, just a quick synopsis. The higher the frequency, the less the impedance or resistance. It's called reactance actually, but whatever. I'm going to call it resistance for right now. So the higher the frequency, the less this resists or impedes. And so if you put a capacitor between here, it makes it so that as the frequency gets higher, the gain boost decreases. So that you're not just, when you're cranking that gain, you're not just boosting the super high frequencies. Doing so can sound really gritty and fizzy and nasty and squealy, and so that's why you see that in a lot of drive circuits. This right here is the gain control. You can see if I turn it this way, that resistance gets larger, so larger resistance, more gain. That sets the minimum amount of gain, that little 100 ohm. You can change that value to set the minimum gain. Okay. And then down here we've got a compression, and it's can be a little bit tough to think through, but this potentiometer here, if I turn it this way, I'm going through that diode and that capacitor there, and if I turn it the other way, I'm going through this diode. Sorry, I should say diode. That's not a diode. That's a transistor. There's a diode in it, but we'll get to that. So it's basically selecting gradually between one type of clipping component and another. Now these are set up to basically limit the voltage output of the system. And so if you limit the voltage output, kind of have a hard limit on that, it distorts the signal. And in this one, and when you're going through here, this is a BS170 MOSFET transistor. It has distortion both ways. It clips both ways. One is through the body diode, which is about 0.7 volts, and the other is through the saturation point of the transistor to turn it on. And that can range. It's a spec that has a range of about 1.3 to 2.0 volts. So, you can drop in different ones and get slightly different results in terms of tonality. But it's an asymmetrical tonality. It's a sweeter tone. And then this is a germanium diode. I usually use 1N34A, but when those aren't available, 1N270 or any germanium diode that's going to have a voltage drop around 0.35, roughly in that volts there. This is only going one way, so it only clips one half of the signal, and by doing so it creates a very strong asymmetrical clipping. It almost is kind of a pseudo octave effect. It's really strong when you crank it all the way. And since it's such a low clipping threshold, it really clamps down on one side and not at all on the other. And so this knob sets the amount of series resistance with that. And so remember, the higher the resistance, the more gain. So basically what that means is when you put in resistance, this doesn't shrink. When it starts to clip, it's not able to pull down the resistance to all the way down to that voltage. It's actually some ratio of that. So basically this ends up being a compression ratio control. So if I turn it all the way there, it's like fully clamping down as soon as I'm exceeding those limits on either side. But if I put a little bit of resistance in there, it's clamping down, just not all the way. So anyway, so that's the soft control. And I wanted to go to this section here. Here's where the fat control is. There's actually two legs in this. In this one, the lower the resistance, the higher the gain. So we got some pretty low resistance resistors, and then two capacitors that are different value. Now, in capacitors, the higher the capacitor, the lower its impedance, or I'll just call it resistance again. So if I have this higher capacitor, what ends up happening is that if I emphasize this one, I'll get more bass response. Okay. And I don't have time to get into all the technical details on that, unfortunately. So because it's a larger capacitor. So if I increase this one, I'm going to increase the overall bass response. So this one right here It's actually if you look at the corner frequency calculations, it's at 1.5 kilohertz. So this is a base roll-off of starting at 1.5 kilohertz. So as the further you go down in frequency, the more that cut is. So it's a pretty aggressive high base cut. So if you just have this one and you take this one out of this line out, it's a very tight, very bright distortion characteristic. And then this just controls how much of this line is getting part of that gain structure. So as it turns this way, you just have 47 ohms. That's lower resistance, that boosts that. And if you turn it that way, it becomes up to 1,000. And so again, higher resistance, it decreases the gain. So feel free to experiment with these capacitor values to how you're mixing sort of the base curve and these minimum resistor values. Okay? And I do recommend an anti-log. This is what C is, taper for that. So that's a nice natural feel to it. All right, let's move on to the next thing. Okay, this is the hard clipping section and the filter section. So after the op amp, it comes out here through a resistor, and that resistor gets shunted to the ground through some diodes. But again, there's this variable compression, just like over there with the op amp. Same idea. I'm just going to be more quick this time. If I turn this way, it goes to these bottom two diodes and shunts to the ground. So it's the threshold's only one set of diodes, so 0.7 volts. They're silicone diodes. And if I turn the other way, it has to go through two of those sets of diodes. So the threshold, clipping threshold, is higher. When you have a higher clipping threshold, it will, one, take more gain to distort. Two, because it takes more gain to distort, you won't get as much distortion or sustain. But because it's not clamping down so hard, you'll get a fuller bass response and a tighter bass response. So you can actually add some more of that sort of fat control and not have it become a complete mess. And I put in a little capacitor here to kind of fiddle with the distortion characteristic. You could probably take that out and have very little impact, but you could also experiment with it with different values. So this right here is just a simple low-pass filter. So a resistor and then a capacitor shunted to ground is a low-pass filter. This just helps vary the frequency of when the treble begins to roll off. So it's flat and then it starts to roll off. What frequency, that corner frequency at which it starts, that's what this controls. So higher corner frequency is a brighter sound. Lower corner frequency rolls off more treble. You get a darker sound. And then this is the last audio stage here. We just simply have a buffer. If you go back to this here, I mean, it's going through quite a lot of resistance, 1K, up to 100K, another 1K. And all these clipping components and such. If you were to attach this directly to a cable and send it, you could have capacitance loading and having your tone affected just by attaching here. So that's why there's a buffer stage. Now, what was weird about the Proco Rad is that this buffer stage had a 10K resistor here, and its potentiometer was here, and it was 100K, which almost kind of defeats the purpose of a buffer. Because if you turn that knob to straight up, if it's logarithmic, you're talking about 85K resistance in the line before it goes out. So capacitive loading is going to be a huge problem. Running into pedals with fuzzes and other things could be I mean, I guess it could sometimes make magic, but most of the time it's going to be a problem. So I switched those. So I took the potentiometer here, so it's a much lower value. So when you turn it down, it's not creating this massive amount of resistance in the output. And then this drop-down resistor here. So we got a coupling cap, another current limiting resistor, another drop-down resistor, and to the output. That's the whole audio section. Here's just a few miscellaneous pieces. These are some decoupling capacitors that I put near active components, particularly active audio components. It's just as a little reservoir of electric charge for when that amp, the op amp or that transistor and the buffer need a little bit more. They can access it more quickly. And then this is just trim pot to adjust the brightness of the LED. And that's it. I will note that there's, well, actually I'll note this later, but all these little pins here have to do with holes in the board that we'll see in a moment. Okay, so here are the pins up top that are connecting. I do want to note that I typically socket this op amp, and the reason is I've had a number of ones, not a ton, but a number of ones that were a lemon, and it was just easier to just pull it out and put in another one. And so that's why I started socketing that part. This 10U capacitor right there, I do want to note it. If you used this is made for a giant film capacitor because of its audio specs are more ideal.